In this video, we're going to discuss ratios within and between similar triangles. The key to figuring this out is to line up the triangles in the same way that they were given to you in the problem. So I can see that ABC and DEF are similar. That's given to me. I'm going to line up ABC with DEF. And what this is going to tell me is it's going to tell me which sides are considered corresponding, which angles are considered corresponding. So the first two angles, AB, will correspond to the first two angles in the second triangle, DE. AB corresponds to DE. The second two angles, BC, will correspond to the second two angles in the second triangle. So BC will correspond to EF. And finally, the first and third angles, AC, will correspond to the first and third angles, DF. So AC corresponds to DF. And I know this because these are the combinations or the order in which they were given to me as similar. So now what I'm going to do is I'm going to set up my ratios to make sure that they are proportional. Okay? So the first thing I'm going to do is I'm going to look at the first question they ask me, which is AB. I'm going to use my chart to see that it must correspond, AB must correspond to DE. And then I'm going to set that up as a side length ratio. So AB I can see is 6, a side length of 6, and DE is a side length of 10. I can then reduce that just like I would with any fraction. I could divide by 2, and that would tell me that they are in a proportion of 3 to 5. Now in the next one, they give me AC. And again, using my chart, I know that AC corresponds to DF. So I can fill that in. I can now use my side lengths. AC is 12, and that corresponds to DF, which is 20. And again, I can reduce these just like I would with any fraction, and it looks like they both share a 4 as a factor, so I'm going to divide them both by 4. 12 divided by 4 is 3. And 20 divided by 4 is 5. And now I have two of them that are in the same proportional relationship, 3 to 5. And finally, I'm going to just check my last one, BC to EF, BC to EF. So yes, those are the corresponding sides that I want to work with, BC to EF. And get those side lengths. BC is 15. EF is 25. I can look at this and I can say, well, if I'm going to reduce them, they look like they both share 5 as a factor. So divide by 5, and this will give me 15 divided by 5 is 3, 25 divided by 5 is 5. Now I can see that all three of them are in a proportion of 3 to 5. All right, now that I know that all sides, corresponding sides, the sides that the problem told me corresponded based on the order in which they gave them to me, since they are all in ratios of 3 to 5, I can now answer part B. So in part B, I'm giving 4 options. The first one, each pair of side lengths compared is in the same ratio. That is true. This is because their side lengths in each pair are lengths of corresponding sides and the triangles are similar. Again, some of that is given information that I have just proven mathematically, so that one is correct. The reason the other 3 will not be, and you'll have to watch and make sure that these don't switch order on you, don't just assume the first one is right, but really read through each explanation to see why the other 3 are not. In the second one, each pair of side lengths compared is in the same ratio. This is coincidence. And nothing that we can prove mathematically is coincidence. If we knew we we had set out to get a 3 to 5 ratio in all of these side lengths, all of these corresponding sides, and we did get a 3 to 5 ratio in all of them, then that is not coincidence, that is mathematical proof. So that's why that one cannot be correct. In the third possible answer, each pair of side lengths compared is not in the same ratio. And so, well, they are, so not in the same ratio. That's right there. We proved that they all are in the same ratio of 3 to 5, so that one cannot be correct. And finally, the fourth possible answer, each pair of side lengths compared is not in the same ratio. And again, we know that that's not a truth. In the third and the fourth one, there is a second piece of information in both of them that would also prove to not be true. And this is because in a proportion, both ratios must be different. No, if they're similar, they must be the same. The ratios must be the same. And this is because the triangles are not right triangles. And the reason that's not true is it doesn't have to be a right triangle. It just has to be a triangle. It does not matter if one of the angles is 90 degrees or not, just as long as we're told they're similar and they line up and they are proportional. It doesn't matter what their angle measures are. So that's a secondary reason in both of those why they cannot be true.